Having discussed aerodynamic drag, let's now consider wheel drag and brake drag. Wheel drag is the friction force between the wheel and the runway and with the wheel bearings, whereas brake drag is the friction force between the brake discs and the brake pads. Wheel drag will come into play as soon as the aeroplane touches down on the runway. However, as friction is a function of the force pushing two forces together, because there is still a lot of lift being generated, wheel load is small during the initial part of the landing run, and therefore wheel drag is also small. As speed reduces and as lift is destroyed by the spoilers, the wheel load increases, which in turn increases the wheel drag. Therefore, wheel drag increases throughout the landing roll and will reach a maximum value just before the aeroplane comes to rest. This image shows that brake drag is by far the most important and the most effective of the various drag forces during the landing, since it provides the greatest retarding force. However, brake drag is only effective if there is also sufficient wheel drag or wheel friction between the tyres and the runway. If wheel drag is low, brake drag will also be low. Consequently, the brakes are effective only if there is sufficient friction between the tyres and the runway. Using this example, we see that during the early part of the landing run, when there is not much load on the wheels and therefore not much wheel friction, brake drag is consequently ineffective in slowing down the aeroplane. However, as the lift reduces and more weight is placed on the wheels, brake drag does become more effective in slowing down the aeroplane. Therefore, brake drag increases as the landing roll progresses. This concept is why pilots need to destroy lift as soon as possible after touchdown, so that the braking action can be at its peak effectiveness early on in the landing. This diagram shows how important the spoilers are in improving the brake drag effect. In most large commercial aeroplanes, however, the braking action may not actually be carried out by the pilots. Instead, it can be carried out by a highly effective automatic anti-skid braking system. This braking system can be set to low, medium or high braking levels, or levels 1 through to 3, and is especially important to use when landing on contaminated runways. These pictures show what happens when the anti-skid system fails and the wheels remain locked. This last part on the discussion of the forces will summarize the drag forces on the aeroplane during the landing roll. The first of the drag forces we discussed was aerodynamic drag. As speed decreases during the landing run, aerodynamic drag comprising of parasite and induced drag decreased. Brake drag, on the other hand, increased during the landing roll as more load was placed on the wheels. Notice that during the early part of the landing roll, aerodynamic drag provides the majority of the drag, whereas once the speed has dropped below 70% of the landing speed, brake drag provides the majority of the drag. The last line on the graph is total drag. From this line, you can see that during the landing roll, total drag increases. Overall, you can see how important brake drag is. If the brakes were to fail, or the landing surface is very slippery, then the loss of braking would cause the landing performance to massively deteriorate, therefore increasing the landing distance. Next, we'll examine what determines the landing distance, and also what roles the four forces play. In order to do this, let's briefly detail the formula that is used to calculate the landing distance. The letter S is the displacement or distance required to stop from a specified speed, which is v, with a given deceleration d. Deceleration is force divided by mass. The force is aerodynamic drag plus the braking coefficient, which is a function of wheel load minus thrust, or in the case of reverse thrust, plus thrust. Expanding the formula in this manner allows you to see how a change in one of the variables has a knock-on effect on the landing distance. We'll now analyse in detail all the factors that can affect the takeoff, with our principal concern being how these factors affect the landing distance. The first of the factors that affect the landing is the effect of mass. Increasing mass has three significant effects on the landing, all of which can be observed in the formula for the landing distance. The first is that a greater amount of mass for a given force applied will reduce the deceleration that the aeroplane can achieve. Essentially, the heavier the object, the harder it is to decelerate it. This is the effect of momentum. More mass will create more momentum. If the deceleration of the aeroplane is reduced, then the landing distance will increase. The second effect is not as apparent as the others. A heavier aircraft requires more lift in order to fly. To get this extra lift, the aeroplane will need to travel faster through the air. This means that the aeroplane will need to decelerate from a higher landing speed. Stopping from this higher speed will require a greater distance, and therefore the landing distance will increase. A third effect of mass is that there will be more load on the wheels, and therefore wheel drag will increase. An increase in wheel drag will allow a greater braking force to be applied. This increases the deceleration of the aeroplane. If the deceleration of the aeroplane is increased, then the landing distance will decrease. In summary, the effect of increasing mass has three effects on the landing performance. Two of them are detrimental, but one is beneficial. The overall effect, as shown on screen, is that increasing the landing mass increases the landing distance. Always ensure that the aeroplane mass is within the performance limitations and never exceed the maximum structural landing mass. Mass calculations are dealt with more comprehensively in the Mass and Balance course as part of the theoretical training. The next factor which will affect the landing performance is the air density. This has two effects. The first effect is that a reduced density means that the amount of reverse thrust produced by the engine is reduced. Reduced engine reverse thrust will decrease the deceleration force, and as a result the landing distance will be increased. The second effect of a low density concerns the landing speed. You will recall that although the landing speed is based upon an indicated airspeed, the true airspeed will be higher in low density. This means that the aeroplane is actually approaching at a faster speed and will therefore require a greater landing distance to stop in. Although the full explanation is outside the scope of this course, high temperatures, high altitudes and high humidity will all decrease the density of air and therefore increase the landing distance. A useful statement to memorize is that high, hot or humid conditions all decrease air density and aeroplane performance.